All right, yeah, I think we're set for today's stream. Let's see what we can do. I'm actually gonna put the gain up a little bit, to be honest. I'm gonna put it up to like 11.6. Let's just see if that's probably good. But let's see. All right, so yesterday we did the execute instructions. We finished all those, and now we kind of did a bit of the memory stage. We had to finish it though. Shouldn't be too bad, and also hopefully do the writeback stage as well, or at least get some of it done. But I think we can get it both done today, both memory and writeback, hopefully. But we'll see. We can start. All right, so we wrote this yesterday, and that looks to be right. And we had to move on. I'm just gonna slowly get rid of them as we go. All right, next is this case. Let's bring it over. All right, so we have the case for load byte unsigned. Looks like we're reading a byte from rs1 and adding it to emit. So we already have that. That would just be our ALU result here. So we can just replace this entire part here. And that's pretty much it. We don't really need to do sign extension since it's not assigned values, it's unsigned values. So we can get rid of this and it will just be a break after. So, yeah, it should be a break after this. Break here. Alright, yeah, that's perfect. Next case, we can get rid of this in here. Next case is load half word. Let's get that in here. Alright, so it looks like that's doing the read half word function. We can do the same thing here. This is pretty much all going to be the same here. Doing the sign extension, but we want to actually we need to change this to mem read. Totally forgot about that. And also get that in here. And get rid of this. So that's perfect. Alright, that's good now. And alright, let me just take a look. Looks like everything's good. Let's take a look now for the next one. Case instruction, load half word unsigned. Okay, let me grab that. Alright, load half word unsigned should be the same. So grabbing that value, putting it in here, and yeah, we're good there. Just have to change this to be mem read. Okay, I think everything's good. Next part. Load word. Alright, take the case for load word now. Same thing. I think it should be pretty easy for these ones. They're pretty much the same. Okay, that's good. Gotta change this to mem read. Alright, that's good. And now we gotta do the next case, which is store byte. So let's do that. Alright, so store byte. So in this case, we're taking an address, and okay, so the address is actually going to be the alien result value, and we're going to be also reading into the rs2 value. So I guess we can take a look at the structure real quick. So in the xmem stage, I guess it just is rs2 value, rs2 floating point value. Yeah, I guess we can write that. Okay, let's see. So that's the alien result. I guess we're already writing it here because there's no destination register to put it into. So I guess we have to write it instead of the load instructions. We're actually loading into a register. This one we're taking that register value and we're taking like the memory, taking the register value and putting it into the offset. So yeah, so we should not wait till writeback. We should immediately do it here itself. Okay, I guess this one will just be address and the value here. Okay, this value I think we can make it as xmem_reg, and I believe it was rs2 value. Just like that. I think it should work like that, and then that should be good. That should accurately reflect our function for that. We could do a quick check though. Just a quick check, make sure everything's looking good. Shadowing bug. I keep forgetting. We gotta get rid of all the Alright, that should be good. Since we already declared that variable, we don't want to redefine it. And I guess we can call this I guess we can keep that same. Did he not have any problems with my store? Yeah, I guess he didn't have any problems with my store. Okay, I just want to know about the store anyways, so. Is there any other bugs other than that? No, okay, looks like everything else is fine then. Alright, okay, yeah, let's move on. Let's just write the last two cases here. Store half word and store word. Alright, let's see. Should be the same result. We can just take these two values and put them in. Instead, we'll just be using this function instead. And same thing here. Yeah, that should reflect it well. Okay, what else? I guess these are fine. I'm gonna delete these now over here. I just needed them as a reference anyways. looks like everything's good. We can move on to the next instructions. I guess the last two would be float load word and float save word. So we're gonna bring these down here. I guess I should have kept my thing here, but we can just rewrite it. I'm just gonna call switch instance.name just to have it here, and then some cases just to have it in here as a reference. Okay. Okay, I think I took the wrong one. Yeah, I took the wrong one. Let's go back. Not that. I took the one from our pipelining stage. That's why I'm not getting anything. Yeah. We need to take one from our actual execute function from up here. Yeah. We need to take them from up here, so we can actually see the stuff we need to implement. That's why I was confused. Yeah. Okay. They're in here now. I guess we can start now. Let's move on. So we have the case of this one. Float load word. And alright, so we had our, we can actually just take a look at our old function up here. It should have stored to a floating point register. Or wait, let me check the spec again. Oh, no, it doesn't store. It does store to the floating point register, but the address we calculated was from an integer register, which is why it reflects that here. So yeah, that's fine. What else? Alright, so we got the offset calculator. That's what we got calculated. So we can pretty much just implement the same how we did. So use the ALU result, which will be this value here. And then we need to actually convert the bits. So we already have that written out. So it's float f. Alright, so we just did nasty pi, and we're doing all the memory. And I guess we can just call this, like, we want this to be the ALUF result. Let me go back up here. Yeah. We do want that to be the ALUF result. And getting the size of these two. Okay, that's good. And then we're not gonna write to the register yet, so we don't need that part, but just these parts. Calculating the memory for it. We're gonna write after. Write a bit later, okay. So we got that one done. Now we need the case for this. Just get rid of that. Alright. This case right here. Float store word. And yeah, it should just be the same. So taking this value here. Okay, we're gonna have the shadowing problem if we initialize. We don't want that to be initialized at all. We just want to use it. But is it not instruct? No, it is. Did I write something wrong? ALUF results, right? Taken from core, memory stage, memory, should work. What's going on here? Oh, okay, I see. Yeah, I see. Yeah, I totally forgot. We need to, since it's from the last step, we need to actually call that on it. I totally forgot. I totally forgot about that. Alright, now it should be fine. I think for simplicity, I'm just gonna low-key just call it, do what I did earlier. I think that'd be better. So we'll just call it float F and have it as that value. So then we can just have what we had earlier. Have F here and then just so it's more readable. What's going on now? Oh, yeah, the reference deleted accidentally. And what else? Oh, semicolon. Okay, everything's good now. Alright, let's take a look at the float store word. Float store word takes the memreg, the alien result. We're also reading the instars too, so we can just copy that in here and call that float F. And this can just be our alien result. ALU results, which will be our from our xmem-reg. Okay. Well, wait. Let me see if I'm even doing that properly. Hold up. So address of that. Storing that into this value right here. Then what exactly? Okay, so we're turning it back to an integer. Let me read this back real quick. Float store word. It's the offset stored into the floating point register of 31.31. Oh, that's interesting. Right. Okay, because we're storing that back into integer memory. So I guess. Value, right, would stay. But let's just take a look. Let's take a look though. Oh yeah. Everything seems to be fine there, but I just want to take a look. Okay, we can store that in here actually, so we can call that here, so we can just call it like, what is the value? ALUF result. Or no, we need so that's from the last stage. We need memread. Yeah, memread. Memory, mzpy, okay, we want that here, and effort. Initialize that in there, and I guess we don't need that here. I guess I misjudged that. So it'll just be student mzpy, but this would be the f-read one. So not an f-read. It's never declared up here. Okay. Couple of hiccups there, but I think you got it. Read, we want to take that and then break. Okay, now for this one, based off what we know, I want to take a look. So we have that, the value, but then I guess we need memory here, right? So we want address of memory here. Size of memory. And we want to write that here too. So it's gonna be like that. I guess. I believe that's how we would do that here. Let me see these. Alright, so we have the address, which is the value result. rs2 value. Oh wait, is it an rs2f value? Let me see. It is an rs2f value, that's my bad. That's my bad on that. rs2f value. What else? The value, oh wait. I guess that was already fine. So we're storing that into that. We don't need to rewrite. Okay. We're not passing it to the next stage anyways. Okay, I see what the issue is for that. Oh yeah, we're not even really reading memory here anyway, so that wouldn't even matter. Yeah, let's do that properly actually. So, value. And value as well. Okay, that's good. And we're gonna get the whole void core now. I guess that I need to continue on now. We need to do the default case now, which will be every other instruction that passes through. So it'll just be a break, essentially. Then we need to, I'll get rid of this, and now we can actually write the remaining parts. Which would be like the next of the values. So we're moving on to a writeback, so it could be this dot inst. Go to the current instruction. Read. Oops, I did that improperly. And that would be the current mem read. What else? So we got the mem read. What else? I guess the bubble itself. And it'll be false if it passes through. Oh, we also need to take the ALU result into the next one too, because we're just passing through. So we want the ALU as well. So we're going to call that. And that would be the current one, right? It would be the current ALU result we have in here since we just passed through. Anyways, this should be a dot, and we forgot reg. Okay. And same for the floating point ALU result as well. We just copy this, it's pretty much the same. F result, F result. And I didn't add that value in here, so let's do that. Okay, it's all good now. I think, right? I think we passed everything. That's all we really need, right? So we have the int, the memory that we got, passing the ALU results, and the bubble. I think that's good. I think that accurately sums up what we needed. I'm gonna send the whole thing to Claude now to confirm that everything is looking good before we move on. Oh yeah, I totally forgot. I totally forgot about that. We do need to pass in the floating point 1 too. I totally forgot. Good call on that. Claude, what else did I miss? Branch resolution. When okay, we're taking the branch. Gonna update. Just push the pipeline. Let me take a look at this back real quick. Alright, so if you're taking the branch, okay, the PC completely gets changed, and okay, let me take another look here into this one. Well, this is for the floating point. Let me get the I instructions. Let me look at branch real quick. What's the offset? Okay. to the PC and flush the pipeline. Okay, I understand the updating the PC part. The flushing the pipeline part. Let me. How exactly do we need to flush the pipeline? I mean, I'm guessing it's because we don't want any more instructions afterwards since we're taking a branch. The remaining instructions would be following the original program counter, I believe, but I just want to double check. Okay. So it's here, branch taken. This plus 4 plus 8. The instruction that comes sequentially after the branch in memory, but if the branch is taken, the CP should be executing instructions at the branch target address instead. Not int plus 4, it's plus 8. Speculatively, CPU didn't know that the branch would be taken when it fetched them. Now that it knows they need to be discarded. So after the pipeline, correct instructions will then be fetched starting from the PC of the branch target in the next cycle. Control hazard. Control hazard, give me a second, guys. I briefly recall control hazards, but I'm gonna check again. I didn't. Oh, no wonder I didn't write it. I didn't write about it yet, so I didn't actually like understand it properly. I think I'll take a look at the chapter 4 guide real quick. I'm just gonna take a quick look in here just to check. Control hazards. Let me just read this part real quick just to get a better idea on it. Take the branch or continue sequentially, but let's keep fetching instructions. Branch resolved in ID stage. Predict not taken. Assume branch not taken. Continue fetching sequentially from flush the fetch instructions and restart from branch target. So I guess that's what we're doing. Essentially, 0 if not taken, 1 cycle penalty if taken. Dynamic prediction. This one seems a bit too difficult. This one seems pretty redundant. It seems like a lot, but it does have a good accuracy. Okay, I'm gonna put this into Claude. See what Claude recommends. Let's see. We could do it Claude's way. Yeah, we're doing the second one. Treatment works well for loops. The branch is usually taken. Well, wait. Better for if statements. Okay. Claude literally said one thing and then said, wait, actually, that's not right. It's the opposite. Okay, predict not taken worked better for if statements, where the branch is often not taken. Okay. Okay, so should I implement it into execute then? Let's see if that's a good idea. Branch outcome after execute. Hi baby, how are you? I'm doing good, I'm doing good. Okay, the trade-off requires comparison target calculation to be done. Execute, if you're already doing an execute, so it's actually set up correctly for. Okay, so I already had it set up. I already had it set up. Okay, let's do it. So we're gonna put it in branch. We're gonna put it into the execute, right? Yeah. Let's put it in execute then. Let's go back up to our execute function up here. We'll do branch resolution right here before we pass on the next variables. Well, we'd actually need it to be after, actually, because we need the next value. Or, I guess we can do the current value, right? That should be fine. I'm just gonna go up real quick to the branch instructions. Oh, I guess we already have the next X now. Values. Okay. So we need an if statement here. And I believe that was like take branch. So if we take the branch here, we need to flush the pipeline and also update the PC. So PC value would be that branch target that we're doing now. And we're also needing to flush that. So what exactly do we need there? So we're only flushing one cycle, we're not flushing two. So earlier Claude said that we need to flush the ID and the IO stages, but now we just need to do the ID. Okay, yeah, just the ID. So now we're reinstantiating it here properly, so it's set to. Okay, it's not right now, but execute stage looks like. Let's see. timing issue. If branch is in X this cycle, what stage is the wrong instruction in? Well, it would just be the if ID, right? Let's give Cloud the whole function. Maybe Cloud's not understanding something. I think he's getting confused. He probably thought I put it into the switch itself. It's outside of the switch, so let's see. Sure, right. Let's trace through it. All right, so cycle n. So we get the new branch value here at this cycle. Once we move on to the next cycle, we're moving to the instruction decode. Oh no, that's 2. That's 2. So flush both. Okay. Well, okay, let's think. If we had it in memory, right, then we'd need to... We'd also need to flush 2 as well, so there's no... Okay, I guess this is taking it from a hardware perspective. Only flushing 1, but we're doing it into code, so we're actually reading from reverse, so I guess... Okay. I guess there's no way around it. We also have to flush this one as well. Alright, that's done. Alright, I'll do the Writeback now. We need to implement it first, so let's go in here and implement that into the struct. We need to call it the Writeback stage. Copy that in, and that's going to be after this stage. Access it from core. All right, let's actually start writing Writeback stage now. Okay, so let's think about what we actually need for the Writeback stage. So, all right, so all we really need is the ALU values to be written to register. We don't need any memory writing for these save instructions, so I think we can just break out of those instructions if they hit that instruction. So I guess we can kind of start writing that part. We'll like keep going and fix stuff as we go. So I guess like, yeah, if the int.name, or I guess we can do it by type, right? They're all going to be S types, so if the int.type is equal to S, we need to create this first though. Go to instruction and make that inst. Alright. But we do need to set the value from the previous writeback stage from here. So it'd be the writeback reg and then accessing the instruction from that. So we do have that. We can also do the bubble as we usually do. So it's gonna be mam.writeback. And bubble like we usually do. Wait, my bad. This should be after memory. I totally forgot. I didn't realize it was over. So if the bubble exists, then just returning, I guess. We're not really executing anything there. We're just returning and starting the next stage again. Okay, what's next? So we have the decode instruction part. So you have insert type. And what's the problem? Oh, I see. I believe, let me check the struct again. It was instruction type. Yeah, we need to access it from the enum. We need to put the scope identifier so we can actually access it properly. Alright, there we go. Alright, so instruction type. It's an S. What else? So S, the other one, the float store word. So I'm gonna call that floating point. We call that floating point S. So we need floating point S as well. I guess this is the only way to do it. It's only a couple, so I guess it's fine. We can implement it like this. FPS. Also, branches don't read, write to register. So B type instructions. What else? Oh yeah, also I guess these instructions at the end here, the eBreak, eCall, unknown, I guess they're called environment and unknown, respectively. Let me go back here. I'm just gonna do this. It says here. So this environment unknown. So if that's the case, it will just be a break, or yeah, I guess just a break, or we'll just say return since it's a function here. Not break. We have to do return. It's a function. I want to check if I'm starting off fine. Handle memory mem. Oh, I totally forgot, yeah. That was a mistake since I copy pasted. And we did upload that in the struct here too. Update that in the struct. Every other stage needs a memory, but this one's just writing back, so it doesn't need anything. Okay, okay. Any other problems? Continue. Okay. Well, I guess now we need to write registers respectively. So we had ALU result and ALU F result. So one writes to floating point register and one writes to an integer register. So we need to actually handle that properly. Let's do that. I guess we can check. We can check if these certain types are actually of the floating point register. If they are, we can actually use them. Okay, I think the best way to do that would be using bool here and just checking the type. Let's just call it like is float. And essentially this one's just gonna be checking for each one to see if we're using a floating point register. Let's take a look here and deduce which one needs floating point registers. If I can remember correctly, floating point load does need a floating point register. Let's go back. It does need a floating point register, so we can check that off. FPL. And we need to denote that with this. Type, my bad, type, not name. Do all of these right? Okay, so let's just go through it. Actually, I think I just need to go through all of them. We know floating point store, we don't need that. Floating point arithmetic, let's see. I think we're just gonna have to go through this and see. Where is it? F-add, yeah, right here. Okay, these do write to floating point registers, so we also need to type for that. So I'm trying to think of an easier way to do this. And I think this really is the best way. It's only a couple checks anyways. I think I just start writing it out and see if Claude agrees. 1 second. Alright, so let's keep moving forward. So if the type is FPA, that's also going to be a floating point register. Or FPR1. So that's the floating point registers that use one register. I forgot exactly what exactly constitutes within that. So let me take a look in here. So the floating point with one register is just the square root one. I believe there's more though. I should have sworn there's more. But okay, yeah. Am I going to check here? Or was it in here? Yeah, it's gonna be in here. FPR1. Okay, I guess there really is just one. There really is just one floating point instruction that uses one register. Okay, that's fine. But let's check if it actually uses that is that square root, right? A square root that is in a floating point register. Okay, square root. Or no, the type is FPR1. I believe most of these do. Fmin max as well. Let's check those. Fmin, yeah, they do. Yeah, they do. Max, FPR4, that's these ones, these type of ones. And they all do go to a floating point register. It seems like. Anyways, if I make a mistake, Cloud will catch it anyways, so. Convent and okay, I think the FP convent is the what is it? Those ones are into integer registers, FP convent, because you're converting floating point to an integer. But these ones, the integer to a floating point, would be where are those ones at? They're over here. Yeah, these ones are floating point registers, so we want to put those into con FP. This is like the best way I can think of right now, to be honest, since there's only a couple instructions. Anything else would be really a lot to implement, but let's see. Fcomp. What was fcomp again? Which instruction did that fall under? Oh yeah, that's the comparison ones. Yeah. And those I believe were to an integer register. Yeah, those are to integer registers, so they don't matter here. But where is F class is here? I need the S one though. F class S. Oh, that's also to an integer register. What did F class fall under though? Floating point to int. Okay, yeah, that's fine then. It will be covered. So I think we did cover. Let's see what we can do now. Okay, so we set a boolean here. It's a set. So if it hits any of these instructions, it's not true. I'm gonna check with Claude on this quick. This instruction FPL, which is in your if flow check, it should be FRB, not ELF result. Handle that case separately. Okay, we will. But we will do that tomorrow, to be honest. We're pretty close. I think, yeah, tomorrow we'll finish up this and we're gonna start writing either the forwarding or the stalling engine. I need to decide which one I'm gonna do tomorrow. But yeah, I have some exams to study for, so yeah, we're gonna end the stream right here.